Now this video explains the example of beam for finding the deflection at point C using the virtual work method. Now this examples has a pin supports at A, roller supports at B, and 4 kilonewton load applied at C. So if I draw the elastic curves, we need to find this deflection at point C due to this 4 kilonewton. Now there are 4 steps. First, we draw the virtual beam by removing all the external load and apply the and then we find the internal moments due to the virtual load. We find internal moment due to virtual load. Let's say virtual load is 1 kilonewton. And then third, we are finding the internal moment due to real loading. And then fourth one, we're going to find the deflections using the equation small m due to virtual load EI dx. Now let's do the first steps. Step number 1, we draw the beam exactly the same A, B, and we are applying this 1 kilonewton virtual load. This distance I did not explain, but in the example it's given 2 meter and 1 meter. Now in this case, first of all, we need to find these reaction forces AY and let's say BY. There is no any horizontal reaction force because there is no any external load. So let's say sum of the moment at point A equal to 0, anti-clockwise is positive. So this is clockwise moment, so 1 times the distance is 3 meters, and this BY create the anti-clockwise moment, so plus BY times 2 meter equal to 0. So BY times 2 meter equal to positive 3 kilonewton meters, and BY equal to 3 on 2 equal to 1.5 kilonewtons. If I do sum of the force in the y direction, upward is positive, AY going up, BY going up, and this minus 1 kilonewton going down. We substitute BY 1.5, so AY plus 1.5 minus 1 equal to 0, so AY equal to 0.5 kilonewton, so AY would be minus 0.5 kilonewton. So I redraw this one here, that here minus 0.5 kilonewton, we have 1.5 kilonewton, and we have virtual load of 1 kilonewton. This is point A, point B, and point C. Now in this case, we need to find small m1 at a distance of x1, so we need to find, let's say, small m1 here, and similarly we need to get this, let's say, small distance x2. We make the second cut and we need to find small m2, and this x1 distance is vary from 0 to 2 meters, and this x2 distance is vary from 0 to 1 meter, because this is 2 meter and this is 1 meter. So if I redraw this cut here, which is minus 0.5 kilonewton here at a cut of distance x1, and I want to find this small m1. In this case, if I take the moment at this point, anti-clockwise is positive and this one is anti-clockwise, so small m1, and this one is clockwise, so minus 0.5 x1 equal to 0, so m1 plus 0.5 x1 equal to 0, so m1 equal to minus 0.5 x1. So that's the first equations that we found. Now the second one that we have it here, which is this cut here. So that cut has a 1 kilonewton, and we are making these cuts here, and that distance is x2, and where we make the cut we have this m2 moment. So again we apply the moment at this point. Anti-clockwise is positive, this is clockwise, so minus 1 x2, and this one also anti-clockwise, minus m2. Minus m2 is equal to x2, so m2 equal to minus x2. So that's we found 2 steps. Third steps, we need to find capital M, which is internal moment due to real loading. Internal moment due to real loading. Now for that case, we draw the beam again. We have this pin, roller, and we have this 4 kilonewton. Now in here, if I have this, if you remember this one, then we can just simplify this one by looking at this virtual load one. That if you can see the virtual load one, we have minus 0.5, we have 1.5, and we have this virtual load of 1 kilonewtons. In that case, if I replicate this one, and if you take the two cut, we found this small m1 value of minus 0.5 x1, and we find small m2 value of minus x2. So if I replicate this one, I can see that 0.5. So I just need to amplify everything by 4. So if I do it here, minus 0.5 times 4 would be minus 2. Over here, if I have to do it, 1.5 times 4, which is equal to 6 kilonewton. Now let's say if I cut it here, and then if I want to find this one, so capital M1 equal to, it gives us minus 0.5 times 4 x1, so that will give us minus 2 x1. Similarly, if I make the cut here, I'm just amplifying everything by 4, so capital M2 equal to minus 4 x2, because that's we have a equivalent loading condition. Now we going to apply our equations to find the deflection equal to 0 to L small m capital L EI dx. Now we have two different segments. So first segments will be vary from 0 to 2. As you can see, this cut is 0 to 2, small m1 capital M1 over EI dx1. Second cut also vary from 0 to 1. As you can see, this cut is 0 to 1. So 0 to 1, small m2 capital M2 EI dx2. Now let's substitute the value. 0 to 2, small m1 is minus 0.5 x1 minus 0.5 x1, that is small m1. Capital M1 is minus 2 x1 over EI dx1 plus 0 to 1. Similarly, M2, small m2 is minus x2, and then we have this minus 4 x2 over EI dx2. Now we can take the common EI, 1 over EI here, and 0 to 2 minus 0.5 times so x1 dx1 plus 0 to 1 minus positive 4 x2 square, and that is 1 over EI and dx2, and this one is x1 square. Similarly, we can take 1 over EI out. Here x1 cubed on 3, 0 to 2. If I integrate that one, I can take the 4 out, and if I integrate this one, x2 cubed on 3, 0 to 1. So simplifications gives 8 on 3 plus 4 EI, it gives us 1 on 3. So here 8 on 3 EI plus 4 on 3 EI, it gives us 12 on 3 EI, which is give you 4 on EI. So deflection at point C equal to 4 on EI. Thank you very much.